So consider the following. Suppose that little p is prime and that big P is a P group acting on a finite set X with cardinality n. Then there is some little x in big X, so that for each little g in big P, gx is equal to x. So let the cardinality of P be equal to P to the alpha. And let P acting on X be any action. Then, by the orbit stabilizer theorem, we have for each g in P, the orbit of G has size P divided by the size of the stabilizer in P at G. Well, what does that mean? That means that any orbit will have size divisible by P alpha. In particular, that means that each orbit must either have size 1, so each orbit can have size 1, size P, all the way up to P alpha. Suppose we choose xi for the ith equivalence class. That is, for each orbit class, we choose exactly one xi. Of which there are k many. That is, there are k many equivalence classes. Suppose that each xi has the size of the orbit at xi is not equal to 1. Then in that case, the size must be some power of P. Then note that the sum of these sizes for each orbit equivalence class will then be equal to the cardinality of X, which is n. But then, since P divides each of these sizes of each orbit, P then divides the total sum, which is now n. So then P divides n, which is a contradiction. Thus, there must exist some xj so that what? So that the orbit of xj has size equal to 1. But note, this orbit, well, what is it? The orbit of xj is equal to g acting on xj, spanning across all g in P. But then this includes, well, what does it include? This includes E times xj. I should say E dot xj, that is the action, which is equal to, by definition of action, xj. However, we had that the size of the orbit is 1. So, for all g in P, g dot xj is equal to xj, which is exactly what we wanted. We found some xj in our set X satisfying this condition.